All right.
All right, guys, thanks for coming. We have the great pleasure of having Eduardo here, and I'm sure it's going to be a very entertaining talk. So I'll let you get started.
All right, thank you very much. So first of all, let me tell you that I realized that my abstract overpromised a bit in terms of I don't know how much time I have for the talk, but in terms of topics, there was a lot there. And I got into like preparing this talk and I was thinking, okay, what would be more important to this audience? I don't know. So in the end, I came up with something. I'll give you a disclaimer at some point of what I will talk about and what I will not talk about. But also, you know, I mean, it can be audience driven. I mean, if you want me to talk more about some other things, I could. Introduction, I'm a professor at the University of Waterloo, applied my department mathematical physics group. And I'm gonna talk about, I mean, in the end, I kind of modified the title to call it like qubits, relativity, and quantum fields. So, oops, now moving. Yeah, so one question that we kind of need to answer first, right? I mean, it's oftentimes even people doing quantum information related or relativity and quantum information related work, is a question that is not often asked. Sometimes it's assumed, right? I mean, what does it mean to put information in quantum field? And we're going to address this. We're going to address this from the point of view of foundations of QFT. And that would be the first thing that we're going to address here. But because I don't know what the background of the audience in terms of pure quantum information versus relativity, etc. So I have a little game here that you may know. I mean, those of you who know this game, or the paradox rather, are not allowed to participate because I'm going to ask a question here. So imagine that we have, so this is what I have here in the background is the land where theoretical physicists live, right? So here you have spherical cows, massless spherical cows, and all that kind of stuff. And I have here in this world, these two squares here represent two rockets. And these two rockets are, of course, identical. They're identical rockets, and they accelerate with the same, when they turn on, they accelerate with the same proper acceleration, both of them. And they're tied by a rope, right? So it's something like this. So we ask a question. Does the rope break or not? So mind this rope is a very weak one, and the moment there's any tension in it, it would break. It would not back react on the rockets, it just would break because it's a very weak, very soft one. Now, and then the why. So, and by why I mean, how do we make phenomenological sense of the answer seen in different reference frames, which is kind of the business of what we call paradoxes in relativity. Quote, paradox means that it looks contradictory, but it only looks contradictory if you don't know quite what's going on. When you actually analyze it properly, there's no paradox, of course. Now, here's there's a reason I'm doing this little game too. So I call the same physics different description. Let's see. So let's just excuse my hyperbolas. I mean, they're not truly hyperbolas. This is just me drawing something. They represent hyperbolas. Those are the trajectories of the two accelerated rockets. And I'm seeing it I'm using something like a launch pad frame, some sort of inertial frame that sees them go. And they follow, of course, hyperbolic trajectories because they're constantly accelerating with the same acceleration. And then somebody looking from the ground would say, okay, so as the two rockets accelerate, they accelerate with the same acceleration. So at different times, I'm going to see the rockets having the same distance between each other, right? Because, of course, I mean, they accelerate with the same acceleration. They're identical rockets. So maybe I would conclude that the rope doesn't break. But now we kind of switch to the reference frame or from the point of view of one of the rockets, and then we write plane of simultaneity for one of the rockets. And then we realize, I mean, again, excuse that I'm not doing the other axis, that would go like that. But you can already tell that the distance between the two rockets, as seen from the first rocket, is increasing in time. Actually, they could call each other and say, hey, look, I'm accelerating 9.81 meters per second square. You should do the same. And the other person is saying, what do you mean? You should do it. You're the one who's accelerating a different acceleration. So they would see each other going further away. So somebody may perhaps conclude in the rocket that the rope would break because the other rocket is going too fast. Now the paradox question here would be, okay, does the rope break or not? What is the right way of looking at this? And usually when I do a poll, I mean, I don't know if you want me to do a poll. I mean, I'll skip it for here. But when I do a poll, it's very interesting. If you poll people who know, people who know, of course, people who know the answer know the answer. But if people don't know this paradox and you poll people who know physics, who don't know physics, right? You get 50-50, which is what you should get. That means they don't know. As a collective, as an ensemble of people, they have no idea, which makes sense because they know they don't know any physics. You know what happens when I ask people who know physics? Typically, the majority answer is the wrong one, which is super interesting because the physicists actually get it, only the other way. The information is there. So the answer, I mean, maybe think without telling me, but think about what the answer is, if you don't know this already, of course. And the answer is, of course, that the rope breaks. So it may be surprising to some people. How do you make sense of it from the point of view of the different frames? So that's what we would call phenomenology here. How do things present according to my understanding of the world? Well, for the accelerated observer A, it's easy. It's because rocket B is faster than us. Even though the two rockets accelerate with the same proper acceleration, because of relativistic, what we would call relativistic effects, the other rocket is accelerating faster than the first one. So therefore puts tension on the strain on the rope, and the rope breaks. Or even from the point of view of the center of the rope, actually at the frame of the center of the rope, you will see the two spaceships pulling the rope in different directions. Now, what is paradoxical, I guess, is, okay, but how do I make sense from the point of view of this guy? Need to go to the animation. The point of view of these guys, right? The guys that were on the launch pad frame, that were seeing the two rockets always at the same distance. It is correct. They see the two rockets always at the same distance. The problem is, of course, that what we have here is an extended object, which is the rope, that is accelerating and moving faster and faster. And the length of the rope, as seen from the reference frame in the lab frame, the launchpad frame, is shorter than the distance between the two rockets. That remains constant. Again, I don't want anybody to understand here that Lorentz contractions break anything, because they don't. What breaks things here is the two rockets pulling in different directions, introducing tensions on the rope. Why did I introduce this? Because this illustrates this little game, if you want, illustrates the fact that, of course, we have something that we call physics. The rope breaks. You cannot go ask people whether the rope is intact or not if you want to use it later, and they say, oh, it depends. This guy would say it's intact. This other person would say it's broken. No, it does break. That's the physics. And then how we make sense of it in different reference frame is what I'm calling here a phenomenology. Let me abuse the word phenomenology to mean that. So let's put quantum in the picture, and let's illustrate the problems that one trivial problem that one has when you try to do quantum information and relativity plays any role. And for that, let me do a little quick review on popular science and how popular science evolved from the 30s to now. This is a real clipping from the New York Times after the Solvay conference and the EPR paper. Einstein attacks quantum theory. Scientists and two colleagues, this is like popular science. So scientists and two other people, maybe that clean the lab or something like that, find it's not complete, even though correct. See fuller one possible. And then believe a whole description of the physical reality can be provided eventually. So you see there's some parts of it that is kind of okay, but then you get the media person, Einstein, and the scientists and two colleagues, who knows who they are, and etc. No, this is how popular science was done. Have we improved from them? Well, maybe, but let me give you an example. I'm sorry, I have nothing. This is being recorded, and I feel bad. I have nothing against Devin Powell, but it does provide for a really good example of bad popular science, this particular headline. So, the race to prove spooky quantum connection may have a winner. Look at this. Particles don't obey the same rules as people. I'm glad that they tell me. Poke a particle, and another one far away can instantly to the touch without any messages passing through the space between, as if the two particles were one. Entanglement is what quantum physics calls the intimate connection. This is, of course, what every time that you get a basic quantum physics course, you have a topic called the intimate connection that talks about entanglement. And now something that is true. Einstein called it spooky. To his dying day, he refused to believe nature could be so unreasonable. That is true. But this is something, there is a notion that is present in many popular science understanding of entanglement that is so at odds with relativity that is really, really a good example to illustrate what problems we have. Of course, problems come, we begin with quantum versus classical correlations. So if I were to put a black ball and a white ball in a bag, and I tell Eugene, pick one, but don't show me. I see that I put the two in the bag, and I say, well, don't show me, please. And then I go far away, say I go to Alpha Centauri or Vienna or somewhere else. And then I'm going to say, you haven't measured the color of your ball, right? No, I haven't looked at it. Okay, but then I look at mine and it's black and I say, oh, yours is white. Whatever happens when you measure, the state of your ball is going to be white. Well, or the opposite, right? Well, yeah, that's not surprising. Nobody would be impressed. Nobody would be spooked by that because, I mean, it's correlations in the color. I put a white ball on a black ball. Maybe what is more surprising is if you pull the same thing with dice, right? If you actually put a set of dice in the ball and then I throw mine and I guess the outcome, if I actually guess the outcome of the person who measures second based on the result of throwing the dice first, then people will say, okay, there's something here that I don't understand well. What's going on? How come that something that is genuinely random or locally genuinely random can be correlated with the outcome of another experiment that is locally genuinely random? Well, that's actually what quantum entanglement is. That doesn't have any classical analog in terms of being able to measure it. Now, the problem here we have is that oftentimes the approach that is taken is the approach of collapse of the wave function, the Copenhagen approach, which is saying, right, when A measures or when B measures, the action of the measurement modifies the state by Luther's rule, applying a projector, and that measurement modifies also the state that is far away. And then people would say, but that's incompatible with relativity. And people would say, no, but nothing travels the information, doesn't travel faster than light. You need to communicate. That's the typical hand-wavy way out of that. But it's really disturbing though. Even, you know, if you go to the foundational side, there's no, I don't care about information propagating. Do I have action at a distance? And is that compatible with relativity? Well, the answer is no, of course, because look, simultaneity is relative. Anything that is based on collapse cannot be compatible with relativity. So imagine that I have at point B here, 3 different observers. One, let's call it V velocity 0. Sees A and C happen simultaneously. They happen at here at time equals 0 at different positions, A and C. And say that A and C, for example, share an entangled state, right? So the measurement for this observer in the middle happens simultaneously at A and C. Nice. But if I consider an observer that is boosted with respect to the other ones, again, observers at B, but that have different relative speeds with respect to the original one, they see C happening before A, and the another observers would see A happening before C. So because of that, any notion, who collapses that? Who pokes what? What are you talking about when you do a state update through Luther's rule? How can you talk about entanglement as some sort of action at a distance, even if, here, let's say that here I'm not talking about anybody communicating anything. From the foundational point of view, there is no way compatible with relativity to understand action at a distance in terms of measuring quantum systems, action at a distance, that is compatible with relativity, because whoever happens, whichever measures first, is definitely an observer-dependent statement. The 3 of them are right. 3 observers here are right in what they're saying in the description of the world. They just have different phenomenology. All right, so far so good? So hopefully I justified why, even from a naive perspective, one has to be careful when one talks about quantum information and relativity, perhaps. And this is without involving QFT yet. All right. Instantaneous action is incompatible with relativity. Fair enough. So let me give you a disclaimer first about the topics, and I feel bad because I know that there's some people here that would love to talk about the stuff that I'm not going to talk about here, but it was too late when I made the preparation of my talk already. I'm not going to talk about the following. Let me illustrate. So imagine that I put, haven't yet discussed what this means, but imagine that I put something here, let's say an atom that interacts with a quantum field, say that this is flat space-time, and I have an atom here, and the circle and the extension on space and time is the extension of the preparation and measurement of the atom. I prepare the atom here, it lives around in this area, and I measure the atom here, whatever that means. And I have another one in the future. Or rather, instead of measurement, think of it as coupling. I put it in a Faraday cage, I open the Faraday cage here, and I let it interact with the field, and I close it back. How about that? Much better. And I do the same for a second atom that is separated from the first one. If I tell you that these 2 atoms start initially in a separable state, even a product state, completely uncorrelated, and I tell you that after interacting with a quantum field, say an electromagnetic field, living in this space-time, they become entangled, maybe most people would not be surprised. Well, yeah, they become entangled because they're allowed to communicate, right? When this one interacts, is allowed to put, if you want, excitations on the field. Maybe you can even call them photons, and they travel at the speed of light, hit this guy, and this guy absorbs them. Of course, they can get correlated and entangled even. Why not? Maybe it's more surprising if I were to do this. I have these two atoms, space-like separated. They are originally in a product state, and after some time, I let them interact with the field. I stop the interaction here, and I ask, what is the final state of these two? Is it still a product state? Is it still an uncorrelated state? Many people would be tempted to say they are, because they're space-like separated. They can't talk with each other, right? In fact, if I were to trace out this atom from, if I have the joint state of the two and I trace out this atom and I get only this one, indeed, this atom, the state of this atom doesn't depend on anything from the first one. This atom has no way to know that this thing is even here, because they're space-like separated. However, though, they do get entangled. And they do get entangled from something that I think is well known in this group or seminar or people, audience, let's say, which is that the vacuum state, not only the vacuum, but the vacuum state in particular of a free field, it's entangled between space-like separate regions. This is well known from long, long ago. It's a very basic result in algebraic quantum field theory. And the interesting thing is that, yeah, we can actually measure and extract and acknowledge this entanglement in physical systems. So if you have two atoms that interact space-like separated, maybe with the vacuum state of a quantum field, maybe what they're doing is kind of swapping that entanglement in a way. They're absorbing that entanglement that was before in the field and now is in the atoms. And that's why they can get correlated with each other even when they're space-like separated. This is interesting for many reasons. One of them is that it gives an operational way of checking field entanglement structure. So if you think of a vacuum state of a theory, you can talk about, okay, sure, I know that there's entanglement in space-like separated regions of the field. It's kind of sad because if I try to measure the entanglement, I get a divergence. And then, well, I regularize in some cases with arguments that are very hopeful, in some cases from fundamental arguments, and I find area laws, and those area laws are connected with fundamental principles of the theory. Well, this gives you an operational way of the entanglement that is actually acknowledgeable, that is actually extractable, which is finite, by the way. You don't need to regularize anything when you talk about the entanglement in quantum fields in terms of things that couple to the field. We will talk about what those things are. Particle detectors, let's call them that couple to the field. And the last thing I want to say about this is that, in fact, you can fully measure all the correlations in a quantum field, and you can think equivalently from the correlations in a quantum field, talk about them from the operational way of having particle detectors, maybe putting qubits in my space-time and let those qubits see the entanglement structure of the field rather than computing it based on calculations that are usually ill-defined and have problems. I will get into this a little bit, not about all the papers that I'm mentioning here. I'm glad that, because like this gives references, but yeah, I will not. I'm gonna go to more fundamental stuff, but this is one important aspect of using if you want, particle detectors approach in QFT. Again, not going to talk much about it, but I will take questions about that, and I have slides. I could even go through them, but time is finite, unfortunately. So memento mori, no? We have a limited amount in this world. So again, I made a choice that this is what I'm not going to talk about here. So what am I going to talk about here? I'm going to talk about what does it mean to put a qubit on spacetime, as I said, and I'm going to talk about communication. All right, so we need to go back a little bit, take a couple of step backs on what does it mean to put a qubit on spacetime to go a very, very fundamental problem, which is the measurement problem in quantum mechanics. And let me quickly summarize the measurement problem. Let me begin. Still an open problem. Of course, the measurement problem, how we get. Let me just summarize the measurement problem as we have a theory that is, in principle, probabilistic from the point of view of predicting single-shot experiments. You can have states that don't have a definite answer of performing a measurement, a single-shot experiment. And yet, we do a single-shot experiment and we get a number. Okay. So that's how this process, how you go from a probability distribution. How we go from a quantum, if you want, probability distribution to a classical ensemble-like probability distribution is a pretty much solved problem. Decoherence tells you exactly how you do that. How you go from a probability distribution to the result of a single shot measurement in quantum, still an open problem that we could discuss, but I'm not going to get into that. I'm going to get into the Heisenberg cut, and I'm going to get into all the subtleties. Let me just say that in quantum mechanics, oftentimes the single shot experiments that answer, we model usually with idealized measurements. Idealized measurements are implemented of non-degenerate, to simplify, non-degenerate observables. I don't care as much about the predictions, because sometimes idealized measurements give good predictions. I'm going to care about the Luther's rule. So what is the rule that updates the state? Because the one thing that we need to do when we carry a measurement is make sure that the state of the system that you measure is updated so that it's consistent with future measurements. And how we do that in quantum mechanics? Well, we say, okay, so we have a rank 1 projector in the spectrum of the measured observable, and then we just project the state on that, and that is the updated state. Now, there are many problems that come with that I said I'm not going to talk about here. The point being that actually you can, if you're not into foundations, of course, you can just not care and still get rich and famous. It's not a big problem from the point of view of an operationalist, somebody that wants to solve problems from the point of view, let's say, of even theoretical problems, from the point of view of not caring about interpretation too much and not caring about the mechanisms or the fundamental mechanisms that give you maybe this effective description of that data in a state with Luther's rule. Cool. Again, I have it twice because this is a big disclaimer. Now, problem gets worse when we consider QFT, when relativity comes into play. Now, to begin with, to do quantum mechanics and relativity together, you need QFT. We can talk a little bit about why I say that. But let's assume, let's take for now that you cannot do relativistic quantum mechanics and you need to do quantum field theory. And we can talk about why if you want, if you have questions. Please do interrupt if there are any questions at any point. This is a very open talk. So we have a QFT now, and maybe we want to measure localized observables of the field. For example, how about the electric field in my room during the duration of my talk? That's a legitimate observable that I could measure. And in fact, it's not unthinkable that when I measure, I get a definite reading. If I have an apparatus here that measures the electric field in my room, maybe I get something like 42 volts per meter. That's reasonable. It's a reasonable value. Now, can I update the field? Can I say that what I've done to the field now I projected on the state of the field corresponding to a field amplitude in my room of 42 volts per meter? Is that something that I can do the same way I did with quantum mechanics? Well, Raphael Sorkin in 1992 said no. Actually, there is a problem. It's called impossible measurements on quantum field. Basically, the summary is, if you want to be consistent with relativity, yeah, you can't. You're going to get inconsistencies if you try to do idealized measurements. Let me explain a little bit the Sorkin problem. So Sorkin in this note in 1992 provides two examples. First, to illustrate what he's going to talk about, and this is an example also because it was 1992. People were not so into quantum info on average. The average physicist was not so into quantum info back then. So this example was actually pretty cool to illustrate one of the things that are behind. He basically said, okay, let's consider a 2-qubit system. Consider a state, let 0A, 0B. Then if you perform a local unitary on A, then make an idealized non-local measurement, that's the point, on the system AB. And then you check the expectation of an observable on B, then the expectation of the observable on B gives information about the unitary that was performed on A. That's a simple example he provides. But that's, I wrote here, surprised. In this room, probably not many people will be surprised, right? I mean, it's quite clear what you did that is kind of like cheating, no? What you did is that the idealized measurement was non-local. You made a projective measurement on a non-local space, subspace. So you actually projected on a Bell state. So that's the thing. This projector allows B to gain information about what happened on A. Now, Raphael writes a second example in which he considers a quantum field, prepares an arbitrary state of the quantum field, then performs a local unitary on the field observable localized around this area A, some local unitary there, then a projective measurement on he doesn't really explain why, but he does a projective measurement on a horizontal slice of spacetime, and then place B, space like separated from A, and then says, look, the expectation of local observables, say for example, the field amplitude on B, gain information about A because I perform this projective. So this is what Raphael Sorkin says, look, we are having here superluminal signaling, something that cannot be compatible with the relativistic nature of the theory. Now, also from the first example, you may be tempted to say, okay, hold on, let me put it like that. The problem is that this is very non-local. Again, same as with the previous example, right? So what about if I localize this? So after Sorkin did that, what happened with people? So people ignored this note. This note was pretty much ignored in the time it was published. People kept using idealized measurements actively and by assumption. And let me emphasize the by assumption. When people talk about, I don't know, when people talk about we have a region of space-time here that has some correlations with this other region on space-time, and we talk, let's compute the out-of-order correlators between these observables, and they compute and they talk about how these correlations are analog to something else, there is an assumption of existence of idealized measurements. I'm not going to get into the details why, but this is very common, still today very common. In high energy physics, it's incredibly common, although they kind of have a pass in regimes that they don't care about relativity in the end. If you go S matrix too much, if you go quantum information, you may care though. But this is something that people kept doing, and still nowadays people do. Now, this is interesting because in RQI, in relativistic quantum information, I was one of those people. When I was a PhD student, I have things out there that use this kind of notion of idealized measurement in quantum fields to do stuff. Now, this was unnerving to many people, and in particular, Faye-Dowker. This is the paper that opened my eyes to this. I didn't know the Sorkin paper until Faye-Dowker pointed it out. And Faye-Dowker pointed it out because in relativistic quantum information, or alleged relativistic quantum information, if you want, people were using projective measurements by assumption. You assume that you can have a qubit prepared in a region of spacetime and things like that. And then Faye just says, I draw attention to the previous work that shows that the observables corresponding to relativistic quantum field modes, commonly employed in papers on relativistic information, cannot be measured by ideal measurements. That's a very polite way to say it. So yeah, there's a fundamental problem and it was ignored. So after Faye's paper, the community became aware of it. And there are two paths that people took. Path number one, I don't care, I'm gonna keep doing what I do, but maybe I'll try to justify why it's actually okay. The other one is particle detectors, what I call particle detectors, which is, I call it that, I mean, don't think of detection of particles, think of a technique in order to talk about how to measure and how to act on quantum fields. Let's take a look at these ones. And the rationale, I'm not gonna quote names or anything. It's gonna tell you what that is. Now, maybe I can get away localizing my idealized measurements goes as follows. Look, the problem is that you're doing a projective measurement that is very delocalized. Same as with example one. If your measurement is localized, you won't have this signaling problem. So maybe it's just that you're being too naive and you are just doing this very long delocalized projective measurement for a reason that you don't know enough. Now, of course, people should have been suspicious that if it's Raphael Sorkin doing this, maybe that he's up to something. So can we solve this issue by disallowing two non-local kinds of measurement? So I put here, naive read of Sorkin's paper may suggest so, right? Because the issue is the non-locality of this projector. Let's take a more modern approach. Here's a paper, it's called Impossible Measurements Revisited. What if we take the physicist wrote and we only measure in regimes where there's no signaling? As in like, sure, you can localize, make your measurements not be in between two light cones or things that are space-like separated, restrict your theory to be only able to do measurements that don't invade anybody's light cones somehow. Can you do something like that naively? Well, that's difficult. And I have this paper, More Ado About beautiful paper, More Ado About Nothing, Michael Redhead, 1994, Algebraic QFT. I have the abstract here because I really like that he asked the questions, what do particle detectors detect? Which is a very, very relevant question for the talk that we have today here. And theorem one in that paper says the following, and it's a difficult theorem to prove. But let's assume that we know the proof. I mean, let's take it as truth, because this is a proof theorem, and says, right, if a projector, this RO, if you want, is the algebra of, it's a wedge algebra, it's the algebra of the observables on a quantum field in a wedge of spacetime. Okay? So this is the algebra of observables of a quantum field in a wedge of spacetime. And this tells me this P, if P is a projector that is in R of O, or is the region in spacetime, then P is an infinite dimensional projector. That's the theorem. Oh, my bad. You see, that's the problem with being recorded. No. R is localized in a region O. I said a wedge. I was anticipating something. No, my bad. Let me rectify. R is the local algebra of a region O in spacetime. Okay? Now, the theorem tells you that if P is a projector in a localized region of spacetime, it has to be an infinite dimensional projector. That's the theorem. Okay, my bad. Now the proof. Right, the proof says that the quasi-local algebra associated with an unbounded wedge of spacetime is a type 3 factor, a von Neumann type 3 factor. Okay, that's a theorem by Dirichlet. Now, any bounded region is internal to some wedge. So by isotony, the algebra of observables in the localized region, in the bounded localized region O, is a subalgebra of some wedge algebra. Okay. Isotony, by the way, is one of the actions of QFT, if you want to build QFT axiomatically. So the projectors in the localized algebra, in the subalgebra associated with the localized region in spacetime, have to be identified with some, it's a subset of the projectors in the wedge. But in a type 3 factor, all the projectors, all of them are infinite dimensional. Conclusion, all the projectors in the localized algebra in a compact region of spacetime are infinite dimensional. How is this theorem messing with us? Well, a projective measurement over a bounded region of spacetime cannot be finite rank. So this notion of getting a 42, you have to give it up. You will not get a definite value. You cannot have anything that is time localized and rank 1. In fact, it has to be rank infinity. An open question that actually looking at myself with a student of mine that's here, Jose Polo, it's what is the compromise? Is there a compromise? Can I have an infinite rank projector, but in a way that is localized in space and time sufficiently well to actually talk about these things? Well, that is an open question that I'm not going to answer here. But you see the problem, right? Reconciling idealized measurements with localized projectors, and those localized projectors cannot be really associated with a Luder's rule that updates the state corresponding to a particular value of a measurement, obtaining a measurement. Any questions so far? Any objections? All right, well, then I'll keep going.
Is there something to be played by the fact that we expect the algebras to be semi-finite?
No.
I mean, like, they should be approximable in like certain ways by finite dimensional.
That's kind of the question I'm asking, right? Like, to what extent? Because the problem with this thing is when you try to see, you talk approximable, in terms of the violations of things that matter for quantum information, retrocausation and superluminal signaling, these kinds of things, the impact of doing these approximations, here's interesting because it's easy to find ways to do it so that in a particular frame, the impact is very small. But when you do it, you mess up with covariance. And when you mess up with covariance means that I can find a frame for where the impact is actually huge. And there's no, how do you estimate how huge impacts are when you're talking about a notion that can only be approximately correct description in a particular frame? Above all, if you talk about something fundamental, which is enabling superluminal signaling, for example. So it's a non-trivial question whether how to approximate, how to talk about this in an approximate way. I'm not saying it's impossible. In fact, I believe it is. I'm saying that be really, really careful when waving hands about the existence of an approximate description of measurements in quantum fields that are based on idealized notions. That's all the claim I'm saying here.
So, like, there's this like kind of well-believed notion that treating things finite dimensionally in QFT with the presence of gravity at least is okay because we expect regions of space-time to be kind of finite dimensional because of Bekenstein-Hawking entropy. And
I don't believe it, because you need to justify the details. So you can say approximately yes, because only some finite sector would actually radiate, right? Everything will be exponentially suppressed and everything will not do it. I don't care. Maybe your exponential tails are compensated by exponential increase of the effects in some scenarios. I don't believe the hand-wavy argument that this is well done. Again, I accept it in the sense, of course, there has to be a regime, but from the point of view of foundations, it's not a good argument. I feel that and the assumption of, this is very often done in gravity. Let's treat the system as a finite dimensional one and you have no problems whatsoever. Because the number of observables that are relevant here is finite, because the effects that go outside of this finite sector are negligible. Well, what I have issue with is how do you define are negligible? In all those cases, there's usually not a good argument in the sense of proving that is negligible. It's assumed that is negligible. And it seems reasonable. I'm not saying it's not reasonable, and I'm not saying those things are wrong. I'm saying that there is a foundational, fundamental problem with them that is not dealt with in those cases. Yeah, and my answer would be, I don't believe it. Why? Why do you know? I believe that there would be exponential suppression of many of those things that go outside of your finite super interesting region. But what tells me that you're not getting violations of covariance that can be exponentially amplified in some particular frames? You can find those. So it's non-trivial to me, waving the hands around this. Again, I'm working on one of the things we're working on is not me only, there's several people trying to formalize these conditions as to when it's okay to consider a finite sector, when it's okay to consider that you can actually work with finite sectors in particular cases in QFTs. And it's a very non-trivial question to actually prove it when it's okay. To give bound estimations on how much error you actually are committing and how much you violate in an arbitrary frame, depending on what kind of frames are allowed and things like that. Just saying it's non-trivial. Okay, maybe I was a bit sensational too, maybe influenced by this article that I posted in Popular Science. But my whole point here is that it's certainly non-trivial and it's certainly not guaranteed. Okay. All right. So let me talk about the other path a little bit. So let me just summarize what is it that I personally want from a measurement theory in QFT. What do I want from it? Oh, by the way, Eugene, thank you for this question. This is the question I wanted from this audience. So I wanted to be capable of producing definite values, right? Because maybe I'm like Valentine and say, and that's okay to be like Valentine and say, I don't care about single shot experiments, they don't exist, just ensembles exist. Well, but imagine that I still want to do single shot experiments. I wanted to be able to produce definite values. I want an update rule. I want to know what measurement my state of the field does to the field. I wanted to be consistent with the theory. That means I wanted to respect causality and many other things I'll talk about in a relativistic theory. And I wanted to reproduce experiments. If it doesn't, then maybe I have a beautiful theory, but I should go home with it. Maybe call it something else. I don't know, string theory, whatever, I don't know. So
that should be row one, right? I mean, number 4 should be number 1, right? Technically.
Yeah, I guess. Well, depending, right? If you're a foundational person, perhaps they're equal footing in a way, and just no particular order in a way. But yeah, definitely has to reproduce experiments otherwise. But you see, you can have a very interesting measurement theory for QFT that is not real, and then you can study what are the mathematical features of them, and maybe learn from them and try to build one that is real. So there's always value about the first 3, I think, alone. Anyway, is there an alternative to idealized measurements? And does the particle detector approach work? What is this particle detector approach that you're talking about? Okay, so I want to stop this because one question that may come to mind is like, hold on, you said that you want to put qubits on spacetime. Why do I care about measurements and detection? Well, actions on quantum fields, any kind of action, preparation of a state, actions on local algebras of the field, they suffer the same problem. If you care about qubits and relativity, you need to make your qubits compliant with the theory. How I put the information on the field has to be in a way that has to be compliant with relativity. How I put it and how I extract it. So let's go to the particle detector approach. So how do we measure quantum fields? Well, in reality, particle detectors, I think it's a very fair description that what we call detection, or things that we use to measure quantum fields, are non-relativistic quantum systems coupled locally to the field. What do I mean by non-relativistic? Because the first argument you can go against, like everything's relativistic, right? I mean, everything's made of quantum fields. Yeah, but if you want to model the human retina, for example, it's pretty much non-relativistic. I mean, the physics that dominate, we know to a very good extent that that system is, to a very good approximation, non-relativistic. So let's put it like this. Particle detectors are going to be very well approximate to a very good approximation, non-relativistic systems that couple locally to the field, but still they have to do it in a way that is compliant and in a way that the non-relativistic nature of the detector doesn't spill on the field and the field theory. So that's what I'm going to talk about first in this talk. So I have Bill Andrew here saying particles are what particle detectors detect. So instead of doing particle physics, talking about a notion of particle in some degree of Fock excitation or whatever, this approach is abandon that. Particle is whatever particle detectors detect. Because single particles are ill-defined, are not localized objects, there are many problems with them. Let's take an approach that is more operationalist in a way. Now, let me just give you a toy model of a particle detector. This is the Andrew DeWitt model. So what is this? So in mind, I have a scalar field phi, and all that I'm doing is I'm coupling some internal degree of freedom of the detector. In mind, it's a qubit. That could be a sigma x, say. I'm coupling some internal degree of freedom of the detector to the field in a region of space and time in a given frame. So you can talk about the coupling strength, the switching function. In a given frame, you can talk about the switching function, how long is the interaction on, smearing function, to what local observable of the field I'm coupling to. You can think of this as a mirror, and we'll see it in a minute. You can think of it like that, right? And say, where is this? Okay, I'll tell you in a minute. So you can think of this as, this is an atom. There are two ways of thinking about that, right? I call it who is who. You can think of it, this is an atom. This is the time evolution operator in that frame that generates the evolution from this Hamiltonian. And you can think of this evolution first as follows. I have here a mu, say, let's call it a monopole moment of the detector. I call it monopole because it's coupling linearly to a scalar field. So I have the monopole moment of the detector, and you can say the monopole moment of the detector is a field itself. And I put the dependence on time and on space in the detector. In a way, it's an atom, right? And we have in a way, the localization of the atom, maybe the wave functions of the atom or something like that. And I assign the spatial localization to the atom. The other way of thinking about it is that the detector actually couples to a observable of the field, saying that this O is a localized observable of the field. Well, an observable of the field, not localized, sorry, some observable of the field Tx, and then integrating over all the points in the field. So something related to coupling the monopole moment to localized observables of the field, indeed. Maybe I should have put the monopole moment outside the spatial integral. But anyway, it's just because there's a time dependence coming from the internal dynamics. That's why I couldn't do it cleanly. But the two options are whether does the spatial smearing belong to the atom or the detector? Does the spatial smearing belong to the field observable that it couples to? But that's your choice. That's a mathematical choice. It doesn't matter. If you're doing quantum optics, you prefer option 1 often. If you're doing foundations of QFT, you prefer option 2 often. Now, this kind of model, can it do all these things that I really wanted from it? What about number 4? Because we'll see these 3 more in detail, but what about number 4? Because as Eugene put it, that's an important one. Well, that's the way charges, to a very good approximation, localized charges coupled to the electromagnetic field through the dipole coupling. And I'm not going to get into that, again, time, but this Andrew DeWitt model that is very simple, you can tell already looking at the Hamiltonians that looks a lot like the monopole version of the dipole coupling to the electromagnetic field. If you want to see references where this is done in detail, these are the references. But you can also consider that, okay, the Andrew DeWitt detector, I'm fine with it, but there are so many detectors that people use in relativistic quantum information, maybe harmonic oscillator detectors, maybe hydrogen atoms. This is taken from Maria, who's here, by the way. This is a slide that she uses, and I just copied it directly. All these variants of detectors that have, the point that they have in common is that they can be related to experimental setups where they predict the outcome of experimental setups. So at the very least, the Andrew DeWitt family of detectors can predict things that happen in the lab. And all of those can be written like this. This generalizes these families of detectors. Now, these are operators on the Hilbert space of the detector. And if you want, you can actually set a two-level system here as your detector, and then you get a qubit detector that couples in a localized way to a quantum field. So here, a way to couple qubits to a quantum field. That is actually consistent with people doing quantum optics and atomic physics. Nice. So far, so good. This is just a way in which we can actually couple things to quantum fields with the objective of measuring. All right. So the one thing that I'm going to talk a little bit more now is to what extent is this consistent with the theory? To what extent doing something like that is consistent with causality in a relativistic theory? There are two aspects that I want to focus on: general covariance and FTL signaling. They are different things. They're not the same. Often, above all, like let's say undergrad level physics, when people wave hands, they're related. They're not. I mean, they're similar. They're related, yes, sure, but they're not the same thing. They're not the same thing at all. General covariance, let me summarize. General covariance is a huge philosophical, so let me just give you my physicist approach to it, tackle to it, because general covariance is a different thing to define. But let me define it as Einstein did. Is that the mathematical representations of a law of physics in different coordinate systems must be connected by the mathematics of coordinate transformations. By that I mean that the the laws of physics should not change because you change the coordinates in which you decide to express the laws of physics. That's what I call general covariance here. No FTL signaling. Well, that's self-explaining. Any model, for example, the detector model that we consider, should not allow for faster than light signaling. And I add the qualifier strong here. Okay, is that understood that this is two things that we definitely desire if we want to use this kind of detector models in QFT and to measure things about QFT? All right, let me give you a quick summary. I'm not going to get into that, but there are ways of building this model. Even though the models that are representing non-relativistic objects, the internal degrees of freedom of those detectors are not QFTs, are not relativistic systems. You can couple them in a way that are respectful with covariance at the very least. So you can have the notion of Fermi-Walker rigidity, which is saying, so think of the detector or an atom at rest. We demand that there are internal coherence forces of the detector that keeps the system approximately rigid in a particular frame. What frame is that? Well, let's call it the moving frame. Say that this atom has a center of mass or something like that. And in that frame, I'm going to demand that the atom is Fermi-Walker rigid, as in like, well, there are internal cohesion forces that will keep whatever the smearing is, are going to keep it solid and rigid. So we demand, so we have here a Hamiltonian density of the interaction. And this Hamiltonian density has a space-time smearing, right? If you talk in a relativistic setup, you don't distinguish spatial smearing from time smearing. It's just a region in space-time, so some space-time smearing. And basically you say, okay, there is one particular frame, which I call the comoving frame with the atom or the center of mass of the atom. And in that particular frame, I can write this Hamiltonian density in a split of a switching function and a smearing function that don't mix with each other. So the space-time smearing factorizes in the comoving frame. That's the condition of Fermi-Walker rigidity. Now, if you impose that condition, you can have that the predictions of the theory are mostly covariant. By mostly covariant, I mean, I'm not going to talk about the details by what I mean by mostly, but at the very least, for all the relevant calculations that you want to do, they are covariant. Now, of course, there's the notion of FTL signals between detectors. Like, what is the influence of one detector over another? If you place two detectors space-like separated, and then you ask, does the action of A can have any information over B? What about if I place another detector here in the middle? Well, here's something interesting. So at leading order in perturbation theory, if you compute perturbatively, the signal, what transmits the information from detector A to detector B, is actually proportional to the commutator of the field at the different supports of the detectors. So if you quantum field theory, regardless of what the detectors do, if your quantum field theory is microcausal, then there is no faster than light signaling between smear detectors, at least at leading order. This is a result in flat in perturbation theory, but you can generalize all these results. let me just quickly summarize papers where this is addressed and solved and to what extent it works. These are papers that I've done with my students. About general covariance, we have Thales and Bruno. And about signaling, we had with Jose de Ramon and Maria Papagiorgio. And in particular, and what are the limitations to those models? And what conditions can we use those models to actually act on fields and to dump information into fields and be respectful with general covariance and not faster than light signaling. The conclusion, let me just summarize it for you, is that for Andrew DeWitt-like models, this kind of detector models, they are okay, as long as you don't do nasty things to them. There are some, let me summarize two common ones. There are more nasty things that you can do. One of them is work on regimes that the detectors don't make physical sense, but other two are very common. They're called the single mode approximation and rotating wave approximation. These two approximations are extremely common in a breadth of scenarios. If in the coupling you do any single mode approximation or rotating wave approximation, you're gonna destroy the relativistic nature of the theory. So that's something to be aware. As long as you don't do those approximations, you should be fine working with detector models in QFT and having a measurement theory based on those from the point of view of relativistic causality and general covariance. Any questions so far? Any comments? Objections? All right. All right. I'm being really relatively fast, but I am willing to slow down as well if need be. I'm of the opinion that being understood is more important than telling a lot. All right. So what about the other two guys? Capable of producing definite values and providing an update rule. Well, extracting definite values, how do I do that? Well, yeah, you can couple the detector to the field. Then do an idealized measurement on the detector, which is okay. Remember the detector is non-relativistic already, so you're not gonna be screwing up anything doing that. And then you update the field state with a consistent POVM that is compatible with the outcome of the PVM that you did on the detector. Here's a protocol and an update rule. And that update rule is, again, strongly compatible with the relativistic nature of the field. Again, there's some work in preparation here with Jose Polo also present here. All right, and then something interesting is that you can now, and this is interesting if you care about gravity, and if you care about entanglement structure in QFT, the expectations of observables on the detector, even if they're qubits sometimes, can inform you of expectations of observables in the field without having to pull any tricks. The nice thing about these couplings also is that they're really immune to spurious divergences that are in the field theory. So really see if the coupling prescription is physical, the detectors don't really see the things that makes the detector, the things that that make quantities like entanglement entropy divergent and things like those. So one example, if you consider a point light detector and log interaction times, directly the expectation value of the energy of the detector, the internal energy of the detector, is directly the Fourier transform of the two-point correlator along the trajectory of the detector in the long time regime. So you're measuring the two-point correlator of the field. Another one, you have several spacely separated detectors. Non-local observables of those systems of detectors are entanglement witnesses from the local algebra of observables of the field. So you can translate statements that are not well defined, or at least they may be defined only in an approximate way. You can translate them from a QFT to something that is finite dimensional and non-relativistic by construction. This is one of the utilities of using these models. All right. So let me give a summary of what I told you so far. What time? Okay, I guess I'm fine. How much time I have? I have another thing to talk about after this. So, Eugene, is there a time limit?
I mean, technically it should be an hour, but I think if you go over time, it doesn't really matter too much.
All right. I'll try to be at least entertaining, and I won't go too much over time. So, again, if one can tolerate restrictions of the regimes where those detectors can be used, then we can have a valid measurement theory with undesired effects under a threshold. So the whole point here is that you can control those effects. You can quantify those effects. I can give you a delta epsilon story about, as opposed to the hand-wavy arguments we talked about, I can give you exactly a delta epsilon argument as to how much I'm being not okay with these things. Now, importantly.
So sorry, Eduardo, I got a little lost on that last remark. What is epsilon and delta? What is the threshold
What I
you're
mean by
talking?
that, okay, yeah, fair enough. I was being stupid. Sorry about that. What I mean by this is that with this kind of approaches, I can actually estimate how much if I use particle detectors and I want to go to extreme regimes when I'm going to start violating, for example, I can get some effects of FTL signaling or some violations of general covariance. I can actually quantitatively estimate how much is it going to be in all reference frames that are relevant to me. For example, I can compute superluminal Fisher information of one detector to another and quantify of if I'm considering a scenario of communication, how much information is actually not kosher in that sense.
No, so this is still in the setting you just described, the particle detector model. Now you're saying there is faster than light.
Okay. Let me go back. There is some, and the sum is related with the non-local coupling of the detector. So the detector, I can show, maybe I show some slides on that. I have some slides on that. So imagine that your detector is localized in a region of space, in space-time here, a region of space-time here. If your detector is just a qubit that is delocalized in space, it's of course violating causality and violating covariance in the sense that it's coupled simultaneously to a bunch of space-like separated points in the field. So in a way—
Sorry, is this a different model than the one you were describing? It looked like you were coupling the detector locally.
let me show you.
Along some world line? Or?
Not really, because I also allowed, when it's point-like, so if the smearing function is point-like, I am. And in those cases, it's completely free of problems.
I see.
If
So
I
that's
did,
the point, that you're considering observables which are actually involve space-like smearing, and that's going to cause signaling.
correct.
Okay.
And the point with those is that that amount of signaling can be under control. So you can, if you want to describe something non-relativistic that's an atom, that is certainly not a point-like system, you can still say, okay, for the setup that I'm considering right now, how much the fact that this thing is space-like separated is going to affect me. One of the results that I don't have here by name, but one of the results is that if you're within perturbation theory, they're not going to affect you a lot. In fact, they're not going to affect you at all in most scenarios.
Mm-hmm.
So this is what I mean by quantifying. We can quantify and telling what scenarios. If you're in a perturbative scenario, no problem. If it's non-perturbative, well, then it depends. In some cases it will, in some cases it won't. And then you have to be clever about how you do it in those cases. So yeah, I was going a little bit descriptive here instead of showing the technical, because I want to talk about communication now. But yes, indeed, where are we? Yeah, indeed, the detectors, what I mean by this particle detector approach, let me just give you a couple claims. If it's a point-like detector, as you said, if you consider your observables to be localized on time-like world lines, then certainly that thing has no problems with causality or covariance. Mm-hmm. If they are mirroring space as well, if it's not time-like, if the detector's mirroring, if the detector times mirroring, it contains space-like separated points, in those cases you might, but in most scenarios that you actually use them for, you don't. You can quantify them, you can see exactly the influence, and I can show you some slides on that. Maybe I should actually show you some slides on that, telling you how much this is quantified. Maybe at the end of the talk, I'll show you some slides on that, how you can actually quantify these things. And you're very safe within perturbation theory. And when not, you can actually tell in what scenarios you're safe.
So if it's potentially problematic to go past perturbation theory, are there potential like experiments that can be done to see exactly what happens in the regimes?
Yes. Oh yeah, certainly. and you know, but the problem with that is that then you have to be careful how you choose your detectors, because those regimes happen to be regimes where detectors tend to not exist anymore. And by that I mean, imagine that I want a measurement that happens in times that are below the light crossing time of an atom. Well, an atom is below those times. The electron won't know if there's a proton there or not in those times. So that's the problem. The regimes in which you start seeing significant violations, either they are regimes in the lab frame, regimes in which your detectors are not good ones, or they are regimes in which you actually try to describe the experiment from extreme reference frames. You boost a lot. To see those, to amplify those, you have to boost, if you want, a lot your lab, right? But yes, you're right. You can find that, and of course it has to fail. We know it has to fail because, you know, turtles all the way down, right? In the end, we don't expect detectors should be described also by excitations of interacting quantum fields and bound states. The problem we have with those is that those are difficult to deal with. So this is more about how much can you get away with these models without having to describe the There is, I haven't mentioned it here, but Chris Fuster at York has this paper that it's called the Fuster-Verge formalism, in which they model detection in considering interacting quantum fields. You have two quantum fields that interact in a bounded region of space-time. And one is considered the detector field, the other one is the probe field. And that works, that violates nothing. That is completely safe from our axioms, right? I mean, all the axioms are untouched by that. The problem you have is, how do you measure the measurement apparatus in that case, if it's also a quantum field? Because the main problem we have is that we don't know how to extract numbers from a quantum field without destroying the quantum field or the relativistic nature of the quantum field. Detectors do provide for those. Again, let me just go back to Eugene's comments. Also, other approaches may approximately provide a valid way of doing this. The difference with the detector approach is in the detector approach, you can quantify in what scenarios you're safe and by how much. The other ones is all waving hands, as far as I know.
So, Edu, maybe a question for me, Grant, by the way. So is the claim then that if you're going to use a smearing function that has some space-like component, that you'll have to, each time you use it, check to see if there's a violation of one of these, let's say, axioms? And you're saying oftentimes in perturbation theory, you're safe. There is no violation, but sometimes there is. And when there is, maybe I misunderstood what you were saying. Was the claim that you can separate how much of some signal of whatever kind you're measuring, you can usually separate that out and say, okay, this part is an effect, but this much is real?
In principle, yes. So again, this is the answer to those questions is in these references too. I'll tell you, but just giving you the references. These two references and this one. There's also an in preparation reference by the same authors here that we're working on right now on this particular way. This one has a little bit of quantification of these effects, but we're doing like more properly done in a follow-up to this. But yes, the idea is precisely that. In these papers, you'll find actually in what regimes you're fine. In what regimes you don't have to actually check because you're fine. And in other regimes outside of that, yes, when you have a smear thing, you may have to be careful, depending on what you're doing with it. Again, this is all about what you're doing with it, but the point is that there are ways to actually check if what you're doing is legit or not. Yeah.
And the even stronger claim is that if you find some any amount of FTL signaling or violation of general covariance, it doesn't immediately invalidate the results. It's just sort of you don't have to throw it away entirely, right? You're saying
not necessarily. The point is in the claim that you have, does the superluminal signaling play a big role in that claim? So if you're claiming, for example, say that you're doing something where it's very relevant. Imagine you're working in entanglement harvesting, space-like entanglement harvesting. You want to really talk about if entanglement in different regions of space-time is following area laws or something, and you use a detector approach. Well, you better make sure that these two detectors are not signaling, because you want them to be correlated out of harvesting correlations already existing on the field, not to get entangled through the interaction with the field. So to the exchange of information through the field. And in those cases, it's really important to know whether you're doing something compliant with FTL signaling or not. Now, if you're a quantum optician and you have an atom and you want to measure if the polarization of a photon is absorbed and if the angular momentum is the momentum of the field and the atom, then you wait for many times the light crossing time of the cavity. You probably are going to be okay. See what I mean? It's all a matter of regimes and how much you care about these effects.
Yeah, I'll take a look at the paper too. Thanks.
All right, no problem. All right, so that's cool. This is what I want. So I really appreciate these kind of questions. All right. Right, okay. So the second part of the talk that I have here is a little bit, I'm not going to get too much again. I prefer to give the ideas than the technical details, but I do have the technical details for those interested. Huh? So let's talk about communication. Now that we've talked, so hopefully I've convinced you, or at least intrigued you, about the possibility that placing qubits in spacetime can be non-trivial, very non-trivial, and it's interesting how these things have changed in time. I remember Faye Dowker in one of the precursors of it from qubits kind of meetings at Perimeter, before that was a thing. Faye complaining when somebody drew, I forgot actually who did it, but somebody drew a qubit and a light cone, and Faye said, what does that even mean? Because well, how do you localize that? How do you localize the information there? How is it that you put it in there? So this is, I have to thank Faye Lauker. Faye Lauker is an inspiration to this work as well. Anyway, so let's talk about wireless communication, because we do it all the time, right? We use massless quantum fields to communicate all the time. Perhaps we don't really use the quantum nature of them, but certainly they are relativistic quantum fields that we use to communicate all the time. All right, I'll give you statements, and then you tell me whether you agree with them or not. I mean, you don't have to tell me, but you think for yourself whether you agree with them or not. If you want to tell me, be my guest. Communication is mediated by real energy carrying quanta. What do I mean by that? An emitter emits photons, a receiver captures photons, in a way. You're emitting energy. If I don't want to use photons because I don't quite like using photons, I would say there's some stress energy density propagating from the emitter and the receiver, and the information is encoded there. That seems uncontroversial, no? I remember Liz Molin once saying, yeah, the information has to be contained in some carrier, right? That has to have some energy, even if negligible, right? There has to be something that carries the information. Okay, uncontroversial enough? All right. Flows are carried by, on average at least, an energy flow. What do I mean by that? Well, information reaches you when the energy reaches you. And why I say average? Because of course I can, for example, with Eugene, I can tell Eugene, oh, Eugene, I don't know if I'll show up to the talk. If I'll show up, I'll give you, if I don't show up, I'll give you a call. But if not, I'm coming. Well, that gives the information. If I'm coming anyways, I don't call him. I don't spend any energy, right? And yet I'm conveying a message. But of course, if I keep doing it every day, sometimes if really, truly I'm conveying any information at all, on average, I'm going to have to spend energy. That's why I wrote the parentheses there. Now, information reaches you when the energy reaches you. That seems reasonable, no? Okay. Connected to this, communication is only possible at the speed of light in vacuum, right? If there's no medium, yeah, the signal goes at the speed of light. Obviously not faster, but also not slower. It's photons. They travel at the speed of light. That also means, by the way, that if you miss the beam, you miss the message. If I get a flashlight and I flash an empty chair and the light's gone away, and then 3 hours later, somebody sits on the chair, you're not going to be able to get the message, right? Everybody agrees with that? Uncontroversial enough? All right, so summary. Communication through massless fields in vacuum, only at the speed of light, through the exchange of real quanta, information flow carried by energy flows, and if you miss the beam, you miss the message. Now, this is the sensational part of the talk. Actually, in general, none of them are true. and kind of difficult, I think, to accept that none of them are true, mainly because I sold them in a very reasonable way, hopefully. And this is interesting because that shows something, some non-triviality of communication with quantum fields. Where does it go? When I talk about qubits and putting quantum information or even classical information in a field and it propagates, where does it go? All right, let me just talk about it. So this comes about, I'm going to talk about one particular aspect of what I just said, which is the subtlety, something classical about the classical solutions, but that manifest in quantum fields very interestingly. So there are subtleties in the behavior of the solutions of certain PDEs. Is what we call the strong Huygens principle. What does the strong Huygens principle say? It says that the Green's function of the massless wave equation in 3+1 Minkowski spacetime has support only on the light cone. Hence, any disturbances propagate strictly along null geodesics, so at the speed of light. Then you can ask, how general is this result? And you can answer, actually, not very general. If you relax any of the ingredients of this, Minkowski spacetime 1+1D, that's not true. The radiation propagator, the radiation Green function, has support in the whole of the time-like area of spacetime. If you go to curved spacetime, same thing. Now, the technical details about this that I'm going to tell you about are in these papers. Now, the one thing that I really want to emphasize is that communication through quantum fields, even if massless, is not constrained by communicating at the speed of light. a communication happens and could happen, there's a time-like echo. When a thought, if you send a signal carried by an energy flow, when that energy is gone, there is a time-like echo, and that time-like echo contains information. And that time-like echo can contain quantum and classical information, both. So this is kind of funny, because that means that if I send information through electromagnetic fields and a beam of information, suddenly there's tails left there. There's information left there that survives. And this is interesting because in 3+1D, which very approximately we kind of live in, you wouldn't see it. But if you relax it a little bit, if you relax it just a tiny little bit, say it's Barfield, as in like, well, no, outside of the surface of Earth, you're gonna see it. Say that you are in an effective 1+1 dimensional system, you're gonna see it. We'll talk a little bit about it, but this is very interesting in many ways. It can affect quantum informational tasks. Imagine that I'm trying to do randomness generation, and I do it by measurement. I'm generating for my casino random numbers, measuring an atom, like preparing and measuring in an unbiased basis. Well, the atom interacts with the electromagnetic field. And when I do that, the atom is gonna dump some information into the electromagnetic field. And you're telling me that maybe the information lingers for a while? Maybe somebody, an eavesdropper, can actually tap into that and use that to gain some advantage on the randomness generation out of that. So those are real problems that you can have in a quantum optical setting based on this, not just fundamental. Also, you can have collect calling in a way, right? Because you send energy. Imagine that I want to broadcast energy to some message to many people. Typically, classically, what you do is you send a huge wavefront. You basically beam everybody with energy. And then these people detect the whatever message it was. But if I want to signal somebody in the future, I can spend energy to send only on the trajectory of my light cone, but then I leave information in the time-like area. Where is that? Oh, I don't have the quantum collect calling paper here. Oh no, it's this one. It's the first one. Sorry, my bad. It's called, we called it quantum collect calling, maybe because, again, sensationalism. Sorry about that. But the reason is that the receiver is the person who pays so if the energy doesn't reach you, extracting the information from the field will come as an energy cost. And very interesting thermodynamic questions come out of that as well. Anyway, so these violations of the strong Huygens principle, when applied to communication through quantum fields, I don't know how much because it's late. I'm going to show you a little problem. This kind of technical details I won't go through, but I'm going to show you a little application problem that is fun, and then we can discuss and get to technical questions if there are some.
So let me ask you something. So the fact that there's like information lingering in a relativistic setting, does that mean things like we traditionally prove, like security of bit commitments and stuff, could potentially be violated in a relativistic setting?
What it means is that maybe some of the assumptions that you make that are not considering what happens in a relativistic setting may not be true. Yes, that's what I mean. So it's not that the proofs are wrong. And if the assumptions that you made in your proofs are very approximately right, then you're fine. But the point is that there are some of those assumptions that may be violated in a relativistic settings. Yes, indeed. The converse is also true. Have Adrian Kent write on bit commitment protocols and the no summoning theorem, as in like sometimes relativity makes things that are insecure in quantum mechanics, make them secure if you also add the constraints that relativity imposes. It goes both ways, and that's one of the beautiful things about relativistic quantum information. That, yeah, it questions some of the assumptions that are often made to prove statements in quantum information theory, but also it gives you extra things that are non-trivial, extra assumptions that may be non-trivial that may help you to do quantum informational protocols and prove they're secure. Yeah, that's the whole problem of bit commitment, right? I mean, no, bit commitment cannot be done classically. What about quantum? Maybe, oh no, it can't. Well, if you add relativity, then you can. And all those things, right? I mean, there are. So I said this is Adrian Kent with the no summoning and Patrick Hayden with the proof that that's actually the case. So there are many of these results that both ways, right? So that's why this I always give us a selling point. Why should I actually care about relativity in quantum both ways? There are two ways we can learn. Indubitably, we can learn about the structure of spacetime and about gravity using quantum information. I need to convince no one for that. But the opposite is also true. We can actually do cool things in quantum information, knowing about relativity. Anyway, let's talk about this example. And that's the last thing I'll tell you. It's a kind of cute example that we did once. So how much information survives And it's related to things about scrambling and thermodynamics and so on. How much information survives a cosmological cataclysm? All right, what is that? So imagine that the universe happens to have some sort of quantum bounds. Imagine that's a real thing. Some theories predict that. Why not? Imagine that cosmologically speaking, the universe is expanding after a quantum bounce, let's say. So there was a big universe that contracted to some regime where quantum effects of gravity cannot be neglected, whatever that is. And they actually provoke a bounce back. The universe bounces back and expands, right? Now, imagine, yeah, that's the thing. I hope that I have the, we'll see. Imagine that that you are, so humans, how long have humans been around? Not a lot. I mean, in the scale of time of the age of the universe, nothing is instantly. We are very primitive still in terms of what we know about the universe for the time that we've been here. And most of what we know, we've learned in the last 200 years or so. So imagine a civilization that existed in a pre-bounce universe and existed for trillions and trillions of years. Very, very intelligent civilization. And they live in that universe and they cracked physics. They know everything about physics because they have enough time to figure out all physics. And they realize that the universe is bound to go through a quantum bounce. Well, that's unfortunately. That's unfortunate. Why? Because atoms, or any complex system for that matter, is not going to survive a quantum bounce. The energy density is the density that you need for quantum gravity effects to dominate. There's no bound system that we know of that could tolerate that. They would all disappear way before that. Or remember, that's the cosmic background. Cosmic background is like, okay, now things can start existing because things are not strongly coupled anymore. So imagine this civilization that existed for trillions of years, and they crack physics to their disappointment, to their despair. They discover that there's going to be a quantum bounce and nothing will survive it. It's like cosmological cataclysm, what I call it. So anyway, we don't know. They're so advanced that it would be very difficult for us to even start to fathom what they would be like. Our best reconstruction would be something like that. But of course, again, we lack a lot of knowledge. So imagine that we have this very, very advanced civilization, and they want their legacy to survive. Imagine, like, you've done amazing things. You've accomplished so much, right? You want it to survive. The question is, all right, so the only thing that will survive here is the quantum fields that that are the fundamental background that imagine that I know there's some quantum fields that will survive, because that's actually a prediction of loop quantum cosmology. The bounce doesn't happen at a scale. I can still consider effective QFTs. Okay, nice. So imagine that bound system will not survive, but quantum fields will. Can I encode how much information can I encode in the quantum field if all that I'm allowed to do is the following? I'm allowed to do encode. I have detectors, I have atoms, I have things that put qubits into the fields. These guys put qubits into the fields by interacting with the kind of interactions we have, like particle detector-like interaction. Of course, they're super clever, and they know how to do it optimally, assuming that at some point after the bounce, there would be a civilization advanced enough to be able to read it. So the assumption here is like, I'm going to do optimal encoding with what I have, and I'm going to do, at some point after the bounce, optimal decoding. So I'm going to assume that somebody will eventually get as advanced as I am and check for remnants of some other civilization there. Then, assuming optimality, we can actually quantify, and this is the power, how much information is recoverable nowadays. I'm going to tell you again, this is a cute example, and I could show you plots, and there are, the point is that yes, you can, not all information is destroyed. And in fact, a lot of information survives. And depending on how much you localize in space-time yourself, like my civilization, is a galaxy spanning civilization, or is it a solar system spanning? Depending on how much you have, you can increase your fidelity of reconstructing these guys. Now, this connects with very fundamental features of a QFT. Now, of course, we know, so if this information we know, are we believers in the larger Hilbert space church or not? I mean, do we believe that quantum mechanics is the way to go? I am. There are people who aren't. So if we believe that is quantum mechanics all the way down, somehow, I mean, some non-trivial quantum, very non-trivial quantum mechanics, but if we believe somehow that it's all quantum mechanics, then information cannot be created or destroyed. We know that. All that we can do to destroy information is scramble it. So the cosmological cataclysm, that's exactly that. A cosmological cataclysm is a scrambler. And it's a very efficient scrambler in some ways, but a scrambler nevertheless that you can figure out. And if you can figure out, or if not figure out, optimally estimate, you can actually pass through a lot of information. So that's why I have this kind of, again, sensational. Maybe you can look at the cosmic background and get these guys back somehow. Anyway.
So if we're here on Earth and we're trying to reconstruct some ancient historical event, couldn't it be that that information got radiated away?
Yeah.
And it's being carried by photons that we can never catch up with, so that information is forever inaccessible to us?
That is exactly, that's a fantastic question. That is where, for example, the violation of the strong Huygens principle plays a role here. Because in an FRTW, Lemaitre, Freeman, Robertson, Walker universe, the strong Huygens principle is violated, and some of the plots that I have, or maybe after this one, some of the plots that I have show you. So you have a detector on, pre-bounce and detector after the bounce, and you have, of course, the information carried. This is actually a channel capacity. We're doing a protocol. We're studying a particular protocol of encoding and decoding with detectors. I can explain the protocol if you want. It's a very innocent protocol. So it gives you a lower bound on the channel capacity you can have between pre-bounce and post-bounce. And you see that, of course, as you say, most of the information goes at the speed of light away from us. But there are tails, at time-like tails. And those time-like tails do not decay with spatial distance. So this is really neat. Those time-like tails, they decay in time. If we wait, for sure, they would decay. Well, it depends also on the universe. If it's at the seater, if it's the seater, they will actually not decay in time either. The moment you deviate from the seater, they will decay in time as well. And that's related with, again, I can show you these propagators. Again, assumptions are made. This is for a matter-dominated universe, so not our current universe. Minimal coupling to gravity. So we consider a quantum field that has minimal coupling to the curvature. So 0 in the coupling to curvature. And the violation of the strong Huygens does not depend on the distance between the events that you're considering. They decay in time, of course, with the scale factor. If you are the seater, though, it doesn't decay in time. These things cancel identically, and it doesn't decay in time for the seater if it's not a matter-dominated universe. So the claim and the point is that there's information in the time-like tails as well. And again, Anthony, you're right. Most of the information lost in light signals, but not all of it because of this remnant. The problem with those is that the information is very delocalized, right? You cannot do it from Earth. You should be able to span a huge amount of space and time to measure and reconstruct. Or maybe be really, really clever about measuring the cosmic background, because in a way, when we measure the cosmic background, we're kind of measuring time-like signals as well through the interactions of that cosmic background with everything else in a very, very large region of space-time. Of course, it's very tricky for me to tell you this without telling you how, right? But this only shows that the information is there, not how to recover it. Anyway, I think maybe I should stop and then take questions because I have so much. And I'm sorry I have so much. I got a little bit carried away. Yeah, thank you. That's it for my talk. Let's leave it there.
I'm kind of interested in the epsilons and deltas for the spacelike smearing.
We'll,
let's say I've got I don't know, it's an atom and it's coupled to the electromagnetic field. And I guess I don't really believe there's going to be faster than light signaling. But if I think of the atom as interacting with, the electromagnetic field smeared over a Bohr radius or something, what do your epsilons and deltas say about the detectable violation of
I can show you. I can show you. Let me give you an example. And for that, indulge me here. Go to archive. Sorry about this. It's cheap, but I prefer the plots for this. And I want the probes in the second page. Causality issues here, that one. By the way, I have to say, advertisement. A paper on the epsilon deltas thing, there's a paper in preparation that's going to come soonish where we do this way better than here. And we actually look at feature information and ability to signal. But still, I'm able to tell you this. This is considering atoms. So if I show you the violations, let's see where they are. All right, there we go. The violations of causality here. The sigma. So let me just explain from the beginning. We have two atoms in space-time, and then we want to, these two atoms start in an arbitrary state. That is, what is the state?
So
Yeah,
we
here.
still see your slides, by the way.
Oh, sorry. Oh my God. Sorry, my bad. I should share another window. Thank you. I was pointing at things on a paper right now. All right, how about this? Now you see the paper?
Yeah.
Okay, perfect. So in this paper, again, as I said, wait for there will be a newer version soonish. Shout out Jose de Ramon and Maria Papageorgiou that are probably here with me. Again, smear coupling, and in mind that that smear correspond to, again, as you said, smear on the Born radius, an atom. And then we prepare an initial state for the detector fields, and that initial state is some arbitrary state for the detector and some arbitrary state for the field, but no, I particularized something else soon. Where is it? Right, this is the signal. Right, I particularized to a product state for the detectors. I consider the detectors originally a product. They're not correlated. And I want to see how much the signal of A couples first in some frame and B couples after. And I want to consider how much signaling there is, how much effect of the presence of A is there in B when they're space-like separated. For that, I compute something called row to signal. What do I call signal? This is a perturbative calculation. When I do this perturbative calculation, what I do is I separate up to second order, and at second order, for the density matrix of the detector after the evolution of coupling with the field, there is a term that goes with lambda A, lambda B, and then what I call the local terms. These local terms, they depend only on lambda A square, lambda B square, and they are just local noise. They don't allow for information to be transmitted for each other. The only ones that allow for information to be transmitted with each other, detected with each other, is the one that is lambda A, lambda B. That's the leading order signaling term. Now, we can estimate how is the signaling term and how much acausal that signaling term is. And we can compute, and we eventually get that this signaling term is proportional to this C function here. And this C, if you see, is a spatially smeared commutator or expectation of the commutator of the field in the regions of coupling of detector A and detector B. So it depends on two things. Is your theory macrocausal? Are you talking about a relativistic QFT? In that case, you know this thing is going to be zero in space-like separation. So the only contribution in space-like separation to this signaling term is going to come through the tails of F and B. So as long as the overlap, and again, it's going to be upper bounded by the magnitude of this commutator. So as long as these two tails, the superposition of these two tails is small enough, and for typical, if you separate maybe 10 times, if you consider atomic wave function, like exponential suppression, and you consider that they're separated by 10 times the Born radius, those things have all the order of 10 to the minus 20 or 25. And if you keep going, you get to 100 really fast, and that a computer cannot even tell the difference. So that is the kind of epsilon delta argument that I'm talking about for these scenarios. You can make it more refined if you go to this other paper. This is gonna be Thales. Let me look. Oh, Rick, of course. Yeah, there we go. You go to the broken covariance one. Again, covariance is a different issue, but it's an issue nevertheless. In the broken covariance ones, you can actually separate in the full evolution of the system at all orders in perturbation theory. This is not a perturbative result in the sense that we limit ourselves to perturbation theory. You can actually, the time evolution, say for the second order one, we do it for all orders, but for the second order ones, you can separate the time evolution into integrals that consider into parts of it that are the ones that are associated with a particular and covariant, the ones that are covariant, if you want, and one that violates covariance. And the one that violates covariance, you can estimate. And as you can see, it's an integral of the commutator of the Hamiltonian density of the coupling. That tells you, again, if the detector is point-like, as you said, right? If the detector is point-like, then it's going to be, the Hamiltonian density is going to be microcausal. And therefore, there's no violations of covariance, of causality. If it's not, how big is it going to be? Well, it depends on the integral or the volume of interaction of these Hamiltonian densities. And we can estimate it and we can check it for an arbitrary order in perturbation theory how much they are, and we see that a second order, it's non-existent, a leading order is non-existent. At higher orders, it would be existent, but we can estimate how strong they are. We can estimate what kind of observables or expectation of what observables upper bound those contributions. So this is what I'm talking about when I talk about a delta epsilon kind of argument. You can talk about what regime in separation and localization you need in. If you tell me, I want to have effects coming from FTL signaling and the localization of my detectors to be below some magnitude for this family of reference frames that are relevant for this particular separation. And then you can compute it, you can give it. Sometimes you can even subtract it, but again, not gonna get there, different story. Hopefully that answers a bit what I mean by that.
I'd like to go back to Eugene's question about, security of crypto.
Mm-hmm.
So you gave the example of Kent's bit commitment protocol, which really isn't quantum. It's a classical protocol where you can use the limitation coming from the speed of light. I mean, do you think there's something interesting to say about, like the Risch-Leader loophole, that because Eve shares some entanglement with Alice and Bob, that there's some limitation on security?
I can tell you, well, this one, I have something to say on the positive side of it, actually using this to be better at transmitting information. But you can also definitely, I'll show you a case where you can use it for bad stuff. So if we go to, okay, maybe I'll describe it. One thing that you can use actually in a paper that was one of the citations that I had in the presentation. The fact that there is entanglement in the ground state of a field can actually be used to enhance communication, and that space-like entanglement, the space-like part, can be used. For example, imagine that I send you a signal. If I send you a signal, that signal is going to be competing, when I read it, it's going to be competing with the local noise of the readout. I measure the field, and they're going to be quantum fluctuations, and those quantum fluctuations are going to be introducing, like not perfect communication. I'm not going to have 1 bit per, if I use qubits to encode a qubit in the field and read out a qubit, I'm not going to get 1 bit per use. It's going to be a lot of noise. In fact, noise dominates because interactions are weak. So you need to send a lot of photons, you need to do a lot of pulses in order to transmit something. However, if you actually measure the field first, you know that the fluctuations, the noise of the field where you are is going to be correlated with the noise of the field somewhere else because of this entanglement in the ground. And when I say ground state, think of a thermostat, same thing. I can use the correlations that even space-like, I can measure later on. I can receive the message. I get the message. It's very crappy. It would be very difficult to get any message. However, now that I'm space-like separated from this person, or even before I make a measurement here. It doesn't touch the message or the protocol, but informs me about the fluctuations that are going to happen that did happen when I read out the system. And I can use the correlations of those fluctuations to subtract the noise. And that noise subtraction increases the signal to noise ratio. So you can use the Risch-Leader kind of loophole, if you want, to improve your signal to noise ratio when you're using a quantum field to communicate, certainly. Now, the counter side. The counter side is not directly Risch-Leader, right? But it's, let me just show you, because I didn't cite this one. Let me just get it. Here. There's this paper that the perspective on it. Let me share screen again. Right, hopefully you see it.
Yeah.
Right. So this is about randomness generation. It's what I talked about. So in particular, you can ask the following in this case. You are generating randomness by considering an atom, and you're going to do this is a legitimate protocol. You do an unbiased preparation measurement on the atom. So you do at some point a preparation by measuring even, and then you measure in an orthogonal basis to that, to the whatever projector you apply. Now, ideally, you would say, right, I know that the atom interacts with the field. So I know that there would be some information leaked into the field of the outcome of the measurement. The state of the field will be correlated with the final state of the atom. It's not going to be a pure state anymore because of the interaction. It's going to be some minimal mixedness on the field. Maybe what I want to do for that, maybe intuitively people would say, okay, so what I'm going to do, I'm not going to be stupid. I know that if I prepare say the atom in an excited state and I let it wait, that's going to decay and put a lot of information into the field. So maybe I don't want to wait for long times. Maybe I want to do it in very short times. I prepare and then I measure. Well, when you measure in very short times, then this delocalization effects of information, this kind of, let me call it relativistic scrambling, even though nothing is really moving fast or anything. But if you do very short time scales, then you are correlating the atom even stronger, in a much stronger manner than when you were waiting a long time. So there's a sweet spot, if you want, of how long to actually wait in order to avoid correlating too much with the field. And in particular, you can estimate how many bits of randomness you can have, assuming that you have an eavesdropper that have access to your field. Imagine that the field is collected. There's an eavesdropper put in a cavity outside your room, and it's just collecting whatever happened inside. That eavesdropper can certainly use the field and the information in the field to reduce your random and cheat you in your casino, for example. Now, how much of that you can minimize, and you can actually design protocols that are going to be optimal for not leaking information to the field. Of course, the regimes in which this happened, right, are very fast and kind of outside of what people usually do. But certainly, those are examples where relativistic protocols can be, or factoring relativity can make things worse, violate some of the assumptions, or it can be used in order to do cool stuff. So yeah, answer is yes, you can certainly. Maybe this is an open, very few things have been done, so an open field for people to actually exploit it and find new ways to do this stuff.
Mm-hmm.
So does it open a loophole for loophole-free Bell inequalities?
I think, I don't know, I don't know about that. So one thing, I mean, if you put a gun to my head and tell me, say something about this related to that, it's certainly a loophole. You can talk about, if you're doing Bell inequality violation with light, certainly going to be entanglement in the field in space-like separated regions. So not even space-like separation. But I would tell you that would be stupidly negligible, because we're talking about imagine a thermal state or a ground state of the field that is coherently the same ground state of the field here and the other side of what I'm doing the experiment. So if you have enough noise, the noise will certainly erase those correlations pretty much so. But yeah, no, in principle, from the point of view of pure foundations, if you want, if you use a quantum field to violate Bell inequalities, you have to be careful that there is entanglement in space-like separation in the field. So it may be blurring your Bell inequality. Maybe that's the entanglement. You maybe are harvesting entanglement from the field, and that's why you're violating things. I guess it should be fine anyways, because in the end you want to prove, it would make it more difficult to formulate. I think you can actually, to be honest, I think that wouldn't be a loophole. You can factor it in and separate it very well from the Bell inequality violation that you get in your observable. So it wouldn't be a loophole. It's rather another contribution to entanglement. There's cool stuff, and it's interesting because I've seen also like Natalie, for example, in the latest papers that also in QFT on the lattice, because people doing fields on the lattice, they have studied correlations in fields on the lattice, and they face similar things and entanglement in those setups, and they're very strongly related as well with things related to entanglement harvesting and this non-locality of correlations in a quantum field, right? In a simple free quantum field. So let alone interactive fields, right? Interactive theories. So there's a lot maybe that can be done out of our knowledge that we have from fields in the lattice, and we can understand more about how these things work in interacting theories, which are highly non-trivial. So I was really happy to give a talk here as well with this audience. Any more questions? So I have a question for audience in terms of like debates and something. How do you feel when people? So I gave you my view, right? But how do you feel about these arguments of when people use finite dimensional systems to make statements and super beautiful results? We know, I mean, I don't know. We know that the results by Geoffrey and all, they're fantastic results, amazing, that I love, but beautiful results. But they do oftentimes are results that make sense enough for finite dimensional systems. Well, quantum fields are obviously not. And there's these arguments that Eugene talked about. How do you feel, Eugene, for example, you've mentioned that. How do you feel about that? Are you convinced by them? Do you accept them?
Well, my prejudice is, that we should always be thinking of an effective field theory, and there's always a regulator, and there's always a finite volume, and we always can approximate any phenomena that we're going to observe. as accurately as we want with finite dimensional systems. So that's my unsophisticated physicist viewpoint.
That makes sense. The one thing that makes me more skeptical, and again, I'm not saying that's not the case. I can find 1,000 examples where that is totally right. But there are some, if you want, ill examples where even having you might not add a soft cutoff somehow, something that is not sharp. And I just consider that there's some effects that things are diluted and blurred, and there's some blurring function. Even in those cases, one can find that there are effects that cannot be transcribed to any finite dimensional theory. Again, it depends on what are you looking at and how you compensate those decays with other things that may grow, right? It's all about that.
My opinion is that, I mean, the argument's certainly a bit dubious using finite dimensional systems, but the results are so nice that it's hard to believe that they're ultimately wrong.
Yeah,
so
yeah.
I see it as a process of discovery, maybe, that we've used maybe perhaps not quite correct arguments to discover correct results, which has to be more properly explained in the future when we better understand these things.
That's actually very convincing, Eugene. Yeah, that's the way I also tend to think about those. So you say more like a kind of Dirac, right? For the Dirac delta in the early times. All right, very nice. Thank you. All right, I don't really have anything else, but I'm happy to answer. I have until 6, something like 6, unfortunately. 6 for me, probably earlier for you, to the top of the hour.
Another 15 minutes, but maybe I'll stop recording now.
Yeah, that's fine. Maybe somebody wants to
some
ask.
memory. If anyone has a last question, now's your time to squeeze it in. Otherwise, thank you, Eduardo. That was truly terrific. Yeah.
People may have questions that want to ask off the record, perhaps. I don't know.
Well, in that case, let me stop recording, and then if you can ask those questions, you can go ahead. All right.
Well,
So
please
let me stop.
continue, but I'm going to have to decouple. But thanks a lot, Eduardo, for the talk.
Oh, thank you for the invitation. Thank you very much.
So long.
Bye-bye. Now is the time to ask embarrassing questions, or even to point out that I was completely wrong. Now is it's a better time.
Let me stop first, I guess.